simple analogy. So in an isolated atom or in a good insulator like salt, the electrons are localized in the atomic sites. On the other extreme, in a very good metal or in free electrons, the electrons move in waves. But it is somewhere in the middle of these two extremes that all the interesting stuff happens, and that's what we work on. So to explain further how it works, if I show you here the energy levels, the energy spectrum of electrons as they are in their different sites, when you are on the insulating side, which is on this area here, each electron occupies orbitals that have discrete energy levels. When you are on the other side here, on very good metals, these electrons, the orbitals start to overlap, and they form wide bands in which the energies form a continuous spectrum. But in this area here, where these bands, these energy bands are much narrower, is where we are talking about. So where are these narrow bands? Mostly they exist in these elements here that are the transition metal oxides and compounds, or in the heavy fermion compounds down here. And these are both either D or F electrons that form these bands that are narrow and very interesting. So the D and F electrons are quite different. In general, the S and P electrons form these wide bands that I talked before, and it's almost like if the electrons are free to move around. And those are most of the textbook physics that you're familiar with. But the D and F electrons form these narrow bands, and they form strong correlations between the electrons. And this is what can lead us to new and unexpected phenomena, like, for example, magnetically mediated superconductivity. So a magnet can have localized electrons, like in the case of insulators, where the spins are sitting in the atomic sites, and if they are ordered in a parallel fashion, then they are a ferromagnet. If they are anti-parallel, like in the lower example, then it is an antiferromagnet. In the case of metals, it is a similar situation, except that instead of being localized, they can move in waves. And so what you are seeing is a spin polarization in magnets, like ferromagnetism in the parallel order, like iron, or antiferromagnetism, like in chromium. So here we have, again, the situation of the different interactions. But basically, magnetism is an inherently quantum phenomenon, and it is a narrow band phenomenon that arises from these interactions. So as you can see here is the same that I mentioned before of the narrow bands, and you can go from one to the other. But in order to study it in the lab, can we drive a system from one area to another in order to study it? And yes, we can. We can do that by the application of pressure. So the motivation for our work in general is to be able to tune these materials. And using tuning parameters, we can move from one state here in this area here, and then we can use a tuning parameter to move it to a different state. So some of the tuning parameters that we can use are like chemical doping, literally just changing the chemical composition of a material. We can also use magnetic field. But pressure gives us a clean tool that is reversible and doesn't introduce any imperfections into the material, which causes disorder when you change the material chemically. In the case of pressure, you can change it and you can drive it into different states, and it's a clean way of doing it. And we can drive a system through metal insular transitions, magnetic phases, or even superconductivity. So examples of these are materials that we have worked on, in which you might have an antiferromagnet to begin with, and then, as you can see here, Tc, that's the transition temperature at which that material becomes an antiferromagnet. With the application of pressure, we suppress that, and eventually we might find a new state of matter. In this case, superconductivity, as in this material, the cerium palladium to silicon 2, in which with 28 kilobars of pressure, we could suppress the antiferromagnetic transition temperature down to an area in which this material became a superconductor. We also have examples of ferromagnetism in which we do the same. We suppress the ferromagnetic transition temperature, and we can then find superconductivity as in uranium, germanium 2. So this is what we try to do, to drive these materials through different phases and try to study the mechanisms that drive this. So you have noticed that I've mentioned superconductivity now several times in these materials, and that's sort of our aim. And I don't know how familiar you are with superconductivity, but you know that up to 30% of the generated electricity in the world gets dissipated in the transmission line. So it depends, of course, on the infrastructure of different countries. I'm not saying that everybody loses 30%, but it can vary, but up to 30% of energy gets lost as heat because of the resistance of the transmission lines. And energy lost as heat is very inefficient. We also lose it in all kinds of electronics, as you're familiar with. And it is the resistance in the material that causes this heat, that causes this energy loss. So superconductors are materials that when you cool them through a transition temperature, the resistance goes to zero. It loses all resistance. And so these materials can conduct an electric current without energy loss. So it really is the holy grail of our kind of work, trying to find the mechanisms that create superconductors and be able to apply them in the real world, in industry and in everything like that. So the superconductivity has the potential to really change the whole industry, energy transmission, electronics, and power grids. Already now, superconductors are being used in medical imaging, like in MRIs and NMRs. They are being used in levitating trains and accelerators. But the problem is that up to very recently, superconductivity was a low temperature phenomenon. So in here, I'm trying to show you the natural elements that are superconducting are all the blue ones, okay? And superconductivity was discovered about 100 years ago in 1911. And they discovered it with mercury. But all of these were found to be superconductors at some point, but all of them very close to liquid helium temperatures. So it's like from 1 to 5 to 6 Kelvin, with the highest of the natural superconductors being niobium with 9 Kelvin transition temperature. So it was something that was interesting but could not be used at all. The green ones that you see here are the ones that they were found to superconduct at very high pressures. So once this happened, we were able to see that there is a potential to understand further the mechanisms and to eventually get to something that can be used in applications. So I'm putting here just to give you an idea of the history that has happened in the last century of all the different superconducting compounds. So here I just have a reminder of what degrees Kelvin versus Celsius, so that you probably already know this. But 0 Kelvin is minus 273 Celsius, and we have liquid helium, which is at 4.2 degrees Kelvin. And so you can see here the first ones here in the very early years of last century were the ones that are already mentioned, which is lead and niobium and tin, and they were all below 10. Then they started to make compounds that could go of the transition temperatures a little bit higher. But in 1986, they discovered what they called at the time high temperature superconductors. And these are these compounds here. And these ones eventually kept moving higher and higher to get to above liquid nitrogen temperatures. And those are the ones that are now being used in these examples that I show you, in which they're using in medical imaging and levitating trains and things like that, because they can actually be kept cold with just liquid nitrogen, which is a lot less expensive than liquid helium. So liquid nitrogen here is at 77 Kelvin. Eventually, they discovered that with very high pressures, you could go higher and higher. And you can see here that 6 years ago, we were already getting to 200 Kelvin. And the big thing last year was that they actually could measure superconductivity at room temperature. But the problem is that it still is at extremely high pressures. So why would we want to continue with this? Because we cannot use it when it's inside a pressure cell, but it is because it shows us the mechanisms. All of these different types of superconductors can take us closer and closer to understanding what is happening at the atomic level of the mechanisms that bring this, and so that we can create new materials. So application of pressure changes the atomic lattice and changes the structure, changing the properties of the material. A simple example, which you might be familiar with, is just pure carbon can exist as graphite, which is a black, soft metal, a good electrical conductor. But with the application of extreme pressures and temperatures, you can create diamond with the same element, which is clear and extremely hard, and an insulator. So this shows you how the application of pressure can change the structure and can change the properties of a material. So what kind of pressures are we talking about, and how do we create them in the laboratory? So here is just to give you an idea of the scale of pressures. At the bottoms of the ocean, you have about 1,000 bar, 1 kilobar of pressure. Diamond anvil cells can go above 4 megabar. And those are the pressures that they used for that room temperature superconductor I showed you. So in our laboratory here in Cambridge, we have much more modest pressures, but the reason for keeping them there is because we actually do measurements that require wires going inside. So this is the principle of all diamond anvil cells in general. So we have different types of cells, which I'll show you. But in principle, all of them have these pistons here that carry a diamond in there. And the diamonds meet in the middle. And we can move the pistons towards each other, as here, and we apply a force. In the middle, we have this metallic disc in which we drill a tiny little hole. You can see it here. And that's our sample space. Our sample space is at maximum in these kind of cells about 0.5 millimeter, sometimes a lot smaller. And then we surround that sample with liquid so that when you apply that force, it creates hydrostatic conditions inside that sample space and creates very high pressures. So this here, I just put it to give you an idea. This is a penny there. And this is the gasket that you see here and a tiny hole in the middle. So this is one of the pressure cells. We have different type of pressure cells in the lab, and some of them are just large enough. This is 18 millimeters, is the one in the previous slide, which we use for resistivity, for AC susceptibility, and we can put it up to 32 Tesla magnet. The next one was created specifically to go into very high magnetic fields because it is much smaller, it's 11 millimeters, and we have taken it in national laboratories up to 45 Tesla magnets. I don't know how familiar you are with what 45 Teslas are, but an MRI, which is supposed to have a very, very high field, is about 5 Tesla, the largest field in an MRI kind of thing, and this is about 45. Here in the laboratory, we have 18, or now we have 20 Tesla, but if we need higher, we have to go to national laboratories to do these measurements. And this cell here was developed in our group specifically to do magnetic measurements. It's much narrower because it goes into a commercially available squid magnetometer and it measures DC magnetization. So we have developed in our group many experimental techniques to be able to do these measurements that I'm talking about. This is one of them, and this is AC susceptibility in an anvil cell. Until this development, it was very difficult to do AC susceptibility on the pressures higher than 20, 30 kilobar. This one, we have taken it up to 300 kilobar of pressure. So what we do is we create these tiny little coils. I put it here just to give you an idea. This one, the diameter of this one is 130 micron coil. They are made with 12 micron insulated copper wire. This one is a bit bigger. And just to give you an idea, this is an eyelash of one of my students, so that you can see how thick that is next to the wires of this. I think that a human hair in average is about 70 microns. And these coils are very, very small. And we put them inside there, and we put a sample in there to measure magnetic phase transitions like here. So with this setup, we have been able to measure antiferromagnetism, ferromagnetism, and superconductivity. It has is very sensitive to any changes in magnetism. This is the other one that I mentioned before that goes inside the squid system, and it can go to about 200 kilobar. And all of them have optical access, so we can actually look through the cells, all of the ones I've shown you, and we can shine a laser through. And inside the sample space, next to the sample, we put a tiny little piece of ruby, which gives us the pressure inside that sample space. So when you have the liquid surrounding the ruby and we shine a laser to it, the ruby fluorescence in the spectrum here gives us the exact pressure inside that space. The other technique that we use is for resistivity. In this case, we have very tiny samples, and we put 4 10-micron wires, gold wire there. We attach them with silver paste so that we are able to then put a voltage to those and then measure, we put a current and measure the voltage here. And by using this technique, here is an example of once it's under pressure, we can then measure from room temperature all the way to low temperatures the changes in the resistance of the material, the resistivity, as a function of temperature, and that's where we can see transitions if it's a magnetic material or if it eventually does superconductivity. So how do we create these very low temperatures? So again, to give you a scale, in outer space is around 3 Kelvin. And I already mentioned that liquid nitrogen is at 77 and helium at 4.2. So often, once we have prepared our experiments and our cells, we put them in a probe, and we can start by cooling it down to 4.2 with liquid helium. But then, using different techniques that we have in the lab, different types of systems, we can cool it down as low as 5 millikelvin. And that allows us, there's a large enough range to study all of these different materials. So now putting it all together, what I want to use is an example of a material because of this material, in a way, we developed a lot of those techniques. This was a several-year project, and thanks to all of those techniques that I showed you, we were able to measure this. It is an interesting material because the structure that I showed you here is similar to those high-temperature superconductors I mentioned before. But this material, calcium ruthenate, has this similar layer perovskite structure with the electrons that have very narrow bands, but the octahedra have distortions. These ones at ambient pressure, in its natural state, is an insulator, and it is an antiferromagnet. And it is due to the fact that these distortions, there's a tilt and a rotation that causes these changes, and so instead of being a metal, it's an insulator. But we discovered soon after starting this project that with application of pressure, with just 5 kilobar, we could actually go through a metal insulator transition. So this is an insulator when you measure resistivity, because the resistivity goes larger and larger. But as soon as we applied a little bit of pressure, we could then make it into a metal. So this metallic phase here, we then measured with our coils that I mentioned before, and we discovered that it had become a ferromagnet. So we have now gone from an insulator to a metal, and from an antiferromagnet to a ferromagnet. And these measurements here can show you the ferromagnetic transition with the coils, and these ones here is with a squid cell. This is a typical signature of a ferromagnet. So with this information, we could start to set up our phase diagram here, in which we plot our transition temperatures versus the pressure we are using. And the way we discovered this is we did neutron scattering measurements, and it showed that this tilt and rotation that was at ambient pressure had now decreased, and that had allowed us to do the metal insulator transition and the different magnetic phase. So the metal insulator transition is with 5 kilobar, and up to 20 kilobar, we discovered also a mixed state in which there were still some antiferromagnetic interactions. So then we continued to increase pressure, and we saw that from 25 to 80 kilobar, we had a good ferromagnetic metal. After that here, we increased the pressures, and eventually we were able to induce superconductivity, which was a big deal for us after many years looking for that. It was at very low temperatures and very high pressures here. So this is about 0.2 of a Kelvin here. I think that the original transition was about 300 millikelvin. And so this was a huge accomplishment for us to be able to take it through there. And it took us at least 5-6 years to do all of that. And so then we could complete our phase diagram here in which we could see that the application of pressure has driven it all the way to a superconductor. So this material is similar, as I said, to others. And you will say, well, why would we be so interested and so excited that we found superconductivity when it is such a tiny little transition temperature? But as I said, this structure is similar to the high TCs and similar to many other superconductors and metals. And so it gives us a lot of information of what is happening in the atomic structure, how you can drive these materials through different phases and through the different magnetic phases too, because we now see that this is a magnetically mediated superconductivity. We have also measured this in other materials now, and we have induced superconductivity in other materials that are very well known now, which have only been discovered about 10 years ago, which is the iron arsenides. They are iron-based materials. The high TCs that I mentioned before are all cuprates. They are all copper oxides. And these ones are ruthenides, which have similar structures and similar properties. So in conclusion, as far as all of this work, is that we have used the high pressure as a tuning parameter, and we have observed metal-insulated transitions, magnetic phase transitions, and pressure-induced superconductivity. So when I was invited to talk to you about my work, they also suggested that I would give you a different type of boundary breaking that I have experienced in my life. So I will tell you a little bit about my journey through the different countries and cultures and different times. And in my life, I've lived through the 60s and 70s in Mexico, and the 80s in Saudi Arabia, the 90s in California, and then here with some France mixed in there. I was born and raised in Mexico City, and then in that time, in the 70s, not a lot of women went to university in Mexico, and my family certainly not. And although, of course, there were a lot of university women, it wasn't as it is now. And I married very young and had children and moved to Saudi Arabia. My husband is from Saudi Arabia. So living there, I was a housewife and a mother. And I wanted to study, but it was complicated. And so I waited. And I was already 30 by the time that we moved to California. And that's when I started college. And I was 35 when I graduated from undergraduate degree in physics in Occidental College, and 37 when I got my master's in UCLA. And then because my kids were still at home and they were still young, I taught for a couple of years. But eventually I made it to England and to Cambridge. And at the age of 45, I graduated with my PhD. And here you can see me celebrating with my grown-up daughters. And so I have continued since then to be here and to continue my research and my work, which is what I have shown you. I guess that the interesting, or the thing that makes it different, is simply that I did all the things that you are doing now, but I was old. So that's what makes it that it has something different, because I was already older. And of course, I've seen a lot of things change in that process and in that journey. As I said, in the 70s, not as many women were going to university, especially not in our countries. And that has changed. All of these changes have happened worldwide. As you know, even women are not driving in Saudi Arabia. So there have been a lot of changes everywhere. And now women having a career and children is the norm, whereas in that time it wasn't. It was more the exception. But I love what I do, and I feel very fortunate to be here and to be able to continue this. And as a woman, I have received also a lot of support. I know that not everybody has found it easy, but I have to say that to do this and to get a PhD at 45 with children, you require a lot of support and help. And I have had that from my mentors and supervisors, but especially my husband, who's been extremely supportive. And now I am a grandmother, but I still enjoy working in the lab and working with the students and working with diamonds and creating high pressures and changing things from a ceramic to a metal by the application of pressure. Thank you.
Thank you so much for that amazing talk. If anybody has any questions, just raise your hand.
Yep.
Thank you for the talk. My question is, if you have proposed some structure of the material, can you predict this critical temperature and critical pressure by theoretical methods?
So there are theories on that, and people do work on theories of different structures and materials. And yes, we are actually now doing things like that. We work closely, we are an experimental group, but we work closely with a lot of theorists who do this. I mean, there are theories that tell you more or less where the transition temperatures will be. And it had been one of the reasons why these new very high temperature superconductors are happening that are hydrogen-based is because many years ago it was predicted that hydrogen eventually with enough pressure could become metallic first and then a superconductor. But that has proven impossible to measure or to create. But these new materials are hydrogen-based. And so that has now been shown in compounds that are hydrogen and different materials. So these new high-temperature superconductors are based on those theories and those calculations, but it's not always easy to produce the material and to then be able to measure it. Because as I said, the record in the world in laboratory of pressures is just above 4 megabars. And that's why it would take a lot more than that to just make it for hydrogen. But hydrogen compounds have now been made, and those are the ones. So the first one that was measured, I think, in 2015 was HS2, and that was a huge thing. But to make that material inside the pressure cell and to create those pressures is incredibly difficult. But a lot of the ones that I show you in that table have been predicted. Every time that a new range of materials comes, it can improve the theoretical calculations because you can show that if you change the structure this way and that way, you will be able to do. So yes, they can be predicted. But then they have to be made, and they have to be made very cleanly because otherwise you have disorder that might not produce superconductivity, and then you have to have these kind of pressures to do it. Yeah. Yeah.
I had a question about the little ring that surrounds the sample.
Yes.
How does that survive? Because you said the entire fluid.
Yes, that's right. So even though it's very delicate copper wire, very, very thin, once it's inside there, the pressure is hydrostatic. So what we call hydrostatic is that the forces are even from every direction in the liquid. So if you didn't have a liquid, it would be destroyed. But the gasket itself is very hard material. We use beryllium copper, and we harden it, so it's very strong. But the liquid itself, as the gasket is trying to hold that in, the liquid is also holding, and it becomes a solid. So with the first 20, 30 kilobar, the entire liquid and everything in there is solidified, and the coil remains in there. Obviously, we end up with endless disasters before we get one to work, because the actual making of the coil is tricky because it's very fine wire, and then we have to move it inside there, and then we have to wire it up outside, and then you put this other diamond on top and break it, and so students take quite a long time to get the hang of it, but once they figured it out, they can do it, and then of course we can get 2-3 pressure points up to certain, and then it breaks, and then you start all over again. It's tedious work, and it requires a lot of perseverance. But somehow it survives. Yeah.
Impressive.
Yep.
Thank you for the talk. So, I want to ask, in terms of theory, what was discovered by your discovery?
In terms of theory, what was, sorry?
Yeah, what was the new insights into superconductivity?
So superconductivity was discovered by accident. It wasn't like a theory. It was, I think, 1911, and this guy Hammerling Ons, he was measuring resistivity. So what had happened is that they already were able to measure resistance of materials and how it decreased. The theories were about decreasing. Nobody knew that something like superconductivity existed. So they discovered it by accident.
So by your discovery of having superconductivity in that new material.
In new materials.
What kind of insights gave to the theory?
Yes. Okay. So most of the insights are related to the interactions between the electrons and these bands and the energy gaps that come with it. So the energy gaps that form between different bands can make it an issue, but also there is an energy gap that creates superconductivity. And so I don't know if you're familiar now with Cooper pairs and things like that. So that's in the theory superconductivity, that's what forms. So in general, you have the electrons and they have a spin and they cannot sit together. But when you transition into superconductor, they form these pairs that they can superconduct all together. So it becomes from a fermion that can only have a spin up and spin down, it can become a boson that they can all be together at the same energy level. So because they have now understood from 1986, from before the theory of normal superconductivity was developed, and then from 86 when the high TCs, they discovered new ways of understanding superconductivity. Since then, all that we do it, and every time that we measure one, we understand a bit more. And in our group, one of the things that changed things was when we realized that a magnet could superconduct. And that was a huge breakthrough. Because the examples I gave you are from magnets, from either an antiferromagnet or a ferromagnet, becoming a superconductor. Originally, decades ago, they thought that they could not coexist. So this is one of the big breakthroughs that we have had to measure magnetic materials that superconduct. Yeah. Any other questions?
Question.
Yeah.
So when you apply like high pressure or high temperature, the order of the structure of the material changes. So is there a way that your group kind of sees like what exactly is changing in the structure?
Yes, you can also do X-rays and neutron scattering. So some of the structure that I show you how it changes, that you can go to national facilities, like we went to Grenoble to do those measurements, and they do neutron scattering that can tell you the atomic structure, the magnetic structure, whereas in other places we do with X-rays, and they can tell you the structure of a material. Even in just normal samples that are not inside a pressure cell, you can just do X-rays, and it gives you the atomic structure. But inside the pressure cells, you have to go other places, and many of them have the facilities to do high pressure neutron scattering or X-rays that can show you the structural changes that we observe. Yeah.
Also, just like adding on to what one of the questions was, is there a way to kind of predict from theory, like based on the material, if that's going to go through a certain order change that is going to be?
So some of it can be. So we work in collaboration. Some of the predictions not always pan out, and some of our measurements don't have a complete theory or doesn't match exactly, but more or less, yes. So things can be predicted, and then we start looking for similar materials that might do something like that. So it is always the experimentalists and the theorists work this way, because sometimes there are predictions that don't come through, and sometimes we have discovered things that nobody predicted before. Like as I said before with superconductivity, they thought that they broke the system because all of a sudden the resistance was zero, right? So it happens like that in many ways, that you measure some huge peak that you don't know what it is, and you think you broke something, or and there is no prediction to that, and then you discover something new. Then you work with the theorists to try to explain it in theory. Yeah. Yeah.
What's so special about the layered perovskite structure that when it deforms, it has a high chance of becoming a
So I don't know if I can understand you with the mask, but you're saying what's special about the perovskite, the layer perovskite materials? So those materials that I show you, that structure is an example of these narrow bands, the d electrons in narrow bands, and the way that they are layered. And this is what was discovered in '86 with the high temperature superconductors. Those copper oxides, like the lanthanum copper oxide, was exactly the same structure as strontium ruthenate, which is without the distortions, and it's a metal and a superconductor. Calcium ruthenate is just a little bit different, that has the distortions. But because we knew that strontium ruthenate superconducted, we thought maybe this other material, the ionic radius of calcium ruthenate, of calcium, is a little bit smaller than of strontium. So that changes a little bit the structure in a way that we thought it would be interesting to see what would happen with pressure. But it was based on the fact that we already knew that strontium luthenate was a metallic superconductor, and that we already knew that that material had the same structure as lanthanum cuprate, which is one of the high temperature superconductors. And we know that that structure, those layer structures of copper oxides, are the ones that many, many years ago were already studied to see that they superconduct at much higher temperatures. So it was a way to measure a similar material and understand the mechanisms involved, and it's the interaction between the layers, the oxygens, how the d electrons form these narrow bands. Yeah.
Yeah, also feel free to come down if you want to ask questions informally.
Yeah, sure.
Yeah, but other than that, thank you so much, Dr.
Thank
Alireza,
you.
for today's
Thank you.
talk. It was really, really insightful.
Thank you.
Could we give another round of applause?
Do I disconnect?